special colloquium this week. So we are going to hear 3 AGU practices from Mark Yu and Jim Bourke and Yucheng Lin. And they are all either grad students or postdocs in our department. So thank you to them for volunteering. And I think they would be, so that we'll do each talk, do a couple minutes of questions, and then we'll move on and then return at the end for questions for everyone. I think they would probably all really appreciate feedback. So if you're listening and have thoughts or ideas that are constructive, then I think they would welcome that. So first up, we have Mark Yu, and he's going to be talking to us about forams from the Maldives. And Mark asked me to introduce him as a final year graduate student.
Thank you, guys. So I'm Mark Yu. Let me double check this works. Good. Today I'll be talking about stratification and surface salinity variations across the last 2 glacial cycles with Maldivian planktonic Foraminifera. And so the Maldives are situated at the heart of the equatorial Indian Ocean. During the summer months, you have a low pressure cell that develops over the Himalayan plateau. As a result, you have cool, moist air that picks up moisture across the Indian Ocean, and it flows from the ocean to land because it's a low pressure cell, because land heats up much faster than the ocean. As a result, you have nucleation, you have condensation, and you have intense precipitation across the summer months on the landmass. As a result, you have upwelling in the Arabian Sea, and you have intense precipitation that flows into the Bay of Bengal. On the contrary, during the winter months, you have the low pressure cell that moves into the Indian Ocean, and you have the wind that change directions, flowing from land to the ocean, and you have moisture precipitation across the oceans. Likewise, you have a reversal of the currents, the surface currents. During the summer months, you have waters that flow from the Arabian Sea to the Bay of Bengal. On the contrary, the winds change direction during the winter months, and you have waters that flow from the Bay of Bengal into the Arabian Sea. The Maldives are situated at the heart between the equatorial, the two end members, the Bay of Bengal and the Arabian Sea. And so the major theme of my study is, can the Maldives capture these seasonal changes on glacial to interglacial timescales? Looking at the CTD, conductivity, temperature, and density profile hydrograph of a modern Maldivian inner seaway, you can tell temperature does not vary across the seasons, right? So looking at temperature, that's in the red and the orange. It does not change across the seasons, and we're in the equator. That makes sense. However, salinity changes by around 1 PSU across the seasons, and that's because during the winter months, you have the fresh waters from Bay of Bengal flowing into the Arabian Sea, reducing the salinity by 1 PSU. We know the monsoons have changed in intensity across glacial and interglacial timescales. Leshker and Soroka in 2003 published a study from the Arabian Sea detailing the strength of the monsoons across glacial and interglacial cycles with sediments from the Arabian Sea. And you can tell, it's due to insolation differences in the amount of heat that the sun generates or it hits the earth. And you can tell precession is the dominant signal. Looking at the spectral analysis, that's because Earth's wobble affects the insolation at the equator the most. And you can tell the 19 and 23 kilo-year band, it pops out the most through the analysis. You can also tell that the intensity of the monsoons have changed across glacial and interglacial cycles, with stronger insolation differences resulting in stronger monsoons. And so what I want to do is we study small forams to understand big concepts. How have the monsoons changed in the past from the forams? And so employing my planktonic Foraminifera records, we measure the stable isotopes at the core top. And so you can tell the mixed layer species, which is the surface, you can tell there's Globigerinoides ruber and Trilobitis seculifer. We also have Neoglobal Cadrina duratri, Polydentina obliquliculata, and Globoratalia monardii, the thermocline species. And so using the paleotemperature equation, we wanted to figure out where they inhabit in the water column. And so from this, we measure the delta-18 of calcite. We have a measured delta-18 of seawater from a previous study. We plugged it into the paleotemperature equation, and we were able to figure out temperature. And I plotted them in the profile, and it matches up with what we expect in the modern ocean, what we observe in the modern ocean. And so knowing this, the core top matches the modern. Can we figure out the past? And so from this, I measured multi-species planktonic foraminifera across marine isotope stages 1 to 6. And you can tell they exhibit the marine isotope stages fairly well. 1, 2, 3, 4, 5A, 5B, 5C, 5D, and then you have MIS 6. From this, you can tell, especially with the planktonic records, they exhibit the glacial interglacial cycles fairly well. However, their ranking, the delta O18 ranking, it kind of fluctuates across these cycles. And so from this, especially with Globigerinoides ruber and Trilobite aculifer, the uppermost layer species, can we figure out, have the monsoons changed in the past from those two species alone? Because they're the ones inhabiting the mixed layer. In addition to stable isotopes, I employ faunal counts. And so thanks to Ronnie Keating for doing the counts, we can tell the most abundant species are Globigerinoides ruber, Saculifer, Deutetribe, P. oblique, and Siphonophora in the assemblage. And it's actually ruber that tends to be driving in red, that's driving a lot of the fluctuations. Overlain with the monsoon index, you can tell, the foram assemblages, they kind of change across glacial and interglacial cycles, maybe with respect to the monsoons. And to focus in on the mixed layer species, I focused in on Globigerinoides ruber and Trilobite aculifer. And so just normalizing everything to ruber, I did ruber divided by ruber plus aculifer to figure out if ruber is driving the differences. And you can tell, there's peaks and troughs, there might be something there. So another way to figure out if it's reflective of the monsoon is to overlay the monsoon index. And bam, look at this. You can tell during strong monsoon intervals, you have more ruber. The abundance of ruber increases when the monsoons are stronger. So in addition to this, I did a linear regression, fairly straight linear regression. You can tell abundance of ruber, there's more ruber when you have stronger monsoons. And so from this, we can tell preliminary conclusion is that the relative abundance of ruber is a good indicator for the intensity of the monsoon, and the Globigerinoides ruber is driving the ratio. I'm running out of time, so I'm going to speed up. Now you can tell the delta O18 record, you can tell the bins, the range of the planktonic species, they tend to fluctuate across glacial and interglacial cycles. In particular, during the colder intervals, they tend to converge and they diverge during the warmer intervals. Observing this, I wanted to figure out if the range and standard deviation can tell us anything about water column structure. So subtract the delta O18 of foraminifera from Claire Walbrook's delta O18 of the global delta O18 of seawater record to figure out the local delta O18. Local delta O18 seawater is basically a function of temperature and delta O18 of seawater, which is basically my monsoon. And from this, you can tell the range is still there. You can kind of tell they change and the standard deviation changes over time. And so what I did is I reduced it to 5 kiloyear bins, and I looked at the standard deviations across that 5 kiloyear, maybe to tell us about stratification. And from this, you can tell that the monsoon index tends to match up with the 1 sigma, in that you have more standard deviation during stronger monsoons. And so interpreting this record, I can tell that during strong monsoons, we have a shallow thermocline. So the standard deviation actually increases. You have low salinity waters from the Bay of Bengal probably, and it induces stratification during strong monsoons. On the contrary, you have a thermocline that steepens during weak monsoons, and you have the forams, they converge a little, and you have more mixing and less stratification during the weaker monsoons. And so I end my talk with a quote from Wally Broker emphasizing the importance of the monsoons, and I hope you guys understand it as well. Thank you. Questions? 10 minutes, that was exact.
Yeah, so you talked before, like you had mentioned about during the monsoons you get that influx of fresh water coming into the Indian Ocean through the Bay of Bengal. I was just wondering, during the glacial periods, like between the interglacials and the glacials, what's sort of the difference between that influx? Is there a noticeable difference between each monsoonal cycle, during those periods versus when when it's a glacial cycle versus an interglacial?
Yes, so the main thing is precession is affecting the monsoons the most. And so precession, if you look at the glacial interglacial cycles, right now it operates at around 100 kiloyears. We're at 100 kiloyear cycles, so eccentricity. I mean, you kind of can break it up maybe into every four precession cycles, you might have a stronger monsoon. So yeah, I would say precession, you would have to look at, you would have to do spectral analysis, and I would have to say, it's probably precession, that's the dominant signal.
I'm just wondering how you want to collect feedback on the presentation.
Yeah, I guess I would suggest if you have feedback to email Mark directly. And, I can send an email out with everyone's email.
I've never worn a wire before.
Maybe you can talk about it.
This
So
goes.
next up, we're going to have James Bourke, who received his PhD this year from EPS. He's now a postdoc, and he's working with Regma. Yeah, so
Cool.
I'll also mention this is an invited talk. So
Yeah, so this is, like Ben said, I wasn't going to go to AGU this year. I was going to go to GSA, and then I got an email in June asking me to present a paper I published in March, as I don't think I'm the final talk in the Central American section, but I think I'm the second to last. So I built this talk based off of the paper. I'm trying to keep it under 8 minutes. I practiced it this morning, and it was 6 minutes. So again, any feedback that anybody has, because I'm going to break my cardinal rule in front of you all right now and just read my notes, because on top of this talk, I also have 2 other posters that I'm currently putting together, so I'm a little bit stretched thin. But I think this is mostly done and should tell a pretty cool story. So I will start real quick just with my notes. Hello everyone, my name is James Bourke, and thank you for coming to my talk titled Caribbean Plate Subduction in Southeastern Costa Rica. I'm a postdoc at Rutgers University, and due to the time constraints of this talk, I'm going to jump right in. I have to click. There we go. So starting with, here's a map of southwestern Central America. We have Mexico in the north, Costa Rica and Panama more central in the map. So currently we have the Cocos Plate subducting beneath the Central American landmass, forming the Central American volcanic arc, which are these orange triangles here. You also have the Cocos Plate bounded to the east by the Panama Triple Junction, with further to the east, the Nazca Plate is subducting beneath South America. In the middle here, you have the Panama Microplate, which is a small tectonic block wedged between the Cocos, Nazca, and Caribbean plates. And lastly, the Caribbean Plate, which is the whole reason we're all here today. And I will go into a little bit more detail on that in the next few slides. But first, I would like to mention a few anomalous geologic observations of Central American region, specifically in southern Costa Rica. First off, we have the Cordillera de Talamanca, or the Talamanca Mountains. These have been rapidly uplifted about 3.5 kilometers in the last 3 million years. They overlie a region of extinct volcanism, which was thought to have gone extinct about 6.5 million years ago. And there's also a lack of typical Benioff zone seismicity, which I'll show a little bit more detail about in the next few slides. Offshore on the Pacific side, we have the Cocos Ridge. Now this is a 20-kilometer thick chunk of oceanic crust. It's formed from the Galapagos hotspot. And currently, it's expected to be subducting beneath southern Costa Rica. However, that really depends on who you ask. Looking more at Panama, to the north, and in this talk you'll see, as of now, for right now, I'm still building it, you'll see some notes. To the north, convergent deformation has been recorded since 1988, looking at earthquake focal mechanisms. Additionally, there's evidence of imbricated thrust sheets in this region. And then looking on Panama itself, there's a study in 2010 by Camacho et al. Looking at the seismicity of earthquakes that exist beneath Panama. And they found a dipping Benioff zone, which is a pattern of earthquakes in depth representing likely a subducting plate, going down to about 80 kilometers depth. This is previously unreported. So looking a little bit more detail of my map here, specifically at transects of seismicity CR to CR primed and P to P primed, what it shows in Costa Rica is you have Benioff zone seismicity dipping from the south to the north,
And then Benioff zone seismicity in Panama dipping from the north to the south. I think this figure alone kind of paints a picture that indeed the Caribbean plate is subducting beneath the Panama microplate. But specifically, our region of interest is southeastern Costa Rica. So the next few slides, I will zoom into this region and talk a little bit more in depth. However, first I want to note that the North Panama Deformation Belt is the north boundary of the Panama microplate, and I forgot to mention this in my notes because I didn't read them. And as you follow this boundary from Panama into Costa Rica, it goes from onshore to offshore, or offshore to onshore, which shows interesting patterns of deformation. Specifically, on the southern portion of the North Panama Deformation Belt here, you have very clear evidence of a thinner basin, imbricated thrust sheets, and evidence of historical seismicity, which is culminated in 1991 with a 7.7 magnitude earthquake in this back arc region. To the north of the deformed belt, up here, you have a basin which kind of would represent a typical kind of back arc extension regime. And the basin there is about 10 kilometers thick, and it was thought to be significantly thicker a few million years ago, but now I'm losing my notes. Now through a bit of the convergence that we're seeing here, it has mostly been uplifted and eroded away. Continuing on. So the methods for the research of this talk is I use the receiver function methodology. To do this, we use teleseismic earthquake data, which arrives near vertical to the recording station. When the P wave hits a interface of changing impedance, some of that energy is converted to S waves. The delay time between those phases gives us insight to where these impedance changes happen at depth. And additionally, the polarity of the phases can tell us whether it's an increase or a decrease in the impedance. So the results of our work can be shown in transect X to X prime. And specifically, I split this region into the Caribbean plate and the Panama microplate, and you can see two very distinct different signatures in the receiver function signal. To the northwest of the deformation belt, we see a very clear signal at about 1.5 seconds, and this would likely be the bottom of that basin I was talking about. Beneath that, we see something a little bit more fuzzy, I would call. However, there is still clear signal there at about 24 kilometers depth. Beneath the Panama microplate, we see a very different pattern of signal in the receiver functions. We see a very clear pulse at about 24 kilometers depth, and this we'd expect to be the bottom of the Panama microplate. And then beneath that, at 34 kilometers, is another strong increase in impedance. And we interpret this as likely the Caribbean plate currently being either underthrust or subducted beneath southeastern Costa Rica. So to wrap this up, this figure is the figure 3 in the geology paper. The major conclusions of this study is that the North Panama deformed belt and the Central Costa Rican deformed belt, which I don't think I defined yet, represent the plate boundaries between the Caribbean plate and the Panama microplate. And additionally, we see the subduction of the Caribbean plate, which is currently taking place beneath southeastern Costa Rica, and possibly occurring throughout the Caribbean coast to Panama. However, this work is still ongoing. I'm now working with Jeffrey Park from Yale University doing synthetic anisotropic modeling of this data and of this region. And I invite you all to come to my poster, which will be in about 30 minutes after I give this talk, titled T13D0258, looking at upper mantle seismic anisotropy in this region. We use a few different more sophisticated tools to looking at the dip of these specific features, and I invite you all to come to look at our new interpretations, specifically how we link these to larger impact and more interesting and anomalous geology and signals that we're seeing beneath specifically the oceanic crust. So that is my talk so far, and I have 10 days to clean it up a little bit, I think, but I'll take any questions now. And please do email me your concerns and stuff. If stuff isn't clear, I have very thick skin. So just bluntly tell me this doesn't make sense and I can change it or whatever. I'm very open to any of that stuff. So, Mike, yeah.
Yeah, what was some of you said there was changes in deformation going from offshore to onshore?
Maybe I just said it not clear because I haven't practiced this enough. What they see is, so to the north of that thick black line, the whole region there is called the Lamont Basin. To the north of that thick black line, they've imaged sedimentary sequences to 10 kilometers, which is fairly thick sedimentary rock package in a basin. To the south of that, it thins considerably. Offshore, they still say it's about 5 to 6 kilometers based off of the offshore shoots they've done. Onshore, they don't really know. There's no onshore seismic, onshore active source seismic data at the resolution to be able to tell for sure the depth of some of these packages. There are some wells drilled in the area that have significantly different heat flow between the north and the south. You know, going across that boundary, the heat flow is double. I think it's 60 milliwatts per meter squared north of the boundary, and it's 30 milliwatts per meter squared south, and they've measured that at a few different wells. But yeah, the deformation itself is extensional north of the deformed belt, but south of that, it's all convergent. And you walk across a region of 5 kilometers or 10 kilometers, and the type of deformation changes dramatically. Yeah.
So how does the Cocos Ridge affect subduction? Does subduction or plate tectonics care whether it's thin oceanic crust or whether it's a thick ridge?
Previous geodynamic work said that any crust over 17 kilometers thick would not be subductible. But I think that's been proved to be incorrect at many, many, many different places. I can say specifically the Pampean flat slab in South America has been imaged clearly 100 kilometers deep, going near vertical. So obviously these can go under, they can be subducted. However, it is a good question whether you have this 20 kilometer thick ridge impacting 30 kilometer thick Costa Rican crust. Is it going under, or is it pushing the whole landmass over top the Caribbean plate, which I think would be technically called abduction? It's a difficult question. However, the seismicity that we see in the region does point to you have the Cocos plate subducting to at least 50 kilometers beneath the Talamancas, beneath central Costa Rica. But the timing of these things is difficult because the Cocos Ridge, some papers say that it had impacted Costa Rica 10 million years ago. Some papers have said it impacted Costa Rica 500,000 years ago. So nobody really knows. And additionally, I have supplemental slides in another pack that I'll add to these. But there's other receiver function studies done in this area that have claimed to see the dipping slab at 70 degrees. And then there's studies like mine that see a more modest dip. And then there's other geomorphic and structural geology studies that are claiming that is, like you saying, more of an indenter than subducting and pushing the whole landmass. And my guess, and after working at this stuff for the last 5 years, is it's probably all a little right. It's probably a mixture of all. I think it's definitely, the Cocos Ridge is absolutely affecting the topography, especially on this. There's a first little mountain belt here, which I can, so it's not very clear, but there's this, this called the Filocostena, I think is how you pronounce it. These are fairly dramatic, like half a kilometer kind of right in your face sheer cliffs. You could stand on the beach of the Pacific and looking up half a kilometer at these rocks. And I think those have been attributed to the subduction of the Cocos Ridge, just uplifting everything. But yeah, it's a question that I don't think anybody really has the answer to. I know our work that we're doing now actually points more to ridge material subducting at least beneath the Talamancas, and some of our measurements of seismic anisotropy really point to this. We're seeing something called slow axis trench orthogonal anisotropy, upwards of 20%, which is really, really strong anisotropic signal. We interpret that as serpentinites at the base of the oceanic crust, and that's part of Jeff Park's kind of running his green dog hypothesis. about underplating serpentinites at hotspot tracks, or hotspot ridges. But that's something I'll go into more detail in a poster, and that will require significant more time to talk about than 8 minutes. I mean, I'm trying to squeeze 95 million years of geology in 8 minutes. So, any other questions? Barry?
Yeah, so if you see the two subducting plates somewhere in how well is that image? How well image is that zone?
Oh, this is a cartoon. So the only things I can say, well, there's a few things. The points, the yellow points here, I would consider to be excellent measurements of something at depth. Now, we've interpreted these some things as we look at seismicity and try to link it to that, look at plate motions and timing. Walther 2003, that's active source on the Cocos Ridge, that's solid. The Arroyo Linkermer 2021 using, and Luque and Arroyo 2015 using seismicity and gravity data, that's pretty solid too. I like a lot of that stuff. My study on the X to X prime, I'll go to war for that. I think I've modeled it synthetically and showing it's dipping in the correct direction. I fully believe that's what that is. In the middle is a lot harder to say. That's the tragedy of non-uniqueness in geophysics, I guess, is technically it could probably be either the Caribbean or the Cocos. We know there's definitely something down there. However, I think the new work that I'm doing, specifically looking at the anisotropic structure, shows strongly that it's the Cocos Ridge that it's imaging to that depth, and that this picture here probably needs to be fixed. I would say here is for certain. Going down to there is a question mark, and this is slowly becoming more certain. But the data quality in this region is tough. The stations are on the top of a mountain that has seismicity on both sides, active volcanoes, and a rainforest. The only way to get there is to drive like 6 hours up a mountain to radio transmitter towers where we installed some of these stations. So it's tough to get instruments. And of course, there's also the cultural difficulty is there are regions in the Talamancas that we just can't travel for cultural reasons. So you have indigenous people still living there. And in some of the field work, we ended up cutting through some of their land a little bit, and I don't think we were supposed to do that. But I think that's more hush-hush for just a joke to tell here and not at a conference of 300 people listening or whatever. But yeah, thank you.
Thanks again. So our last speaker is going to be Yucheng, Dr. Yucheng, also a postdoc at EPS. And we're just going to get Yucheng's talk loaded up.
Oh,
I'll mention, I emailed everyone email addresses for all three speakers if you'd like to feedback. And I'll also mention we have one more colloquium this semester. Emily Ching will be speaking next Wednesday. She is the MSA Distinguished Lecturer, and so she's coming to us from Scripps. And also next week is the holiday party. So
the wire.
Also the microphone. Thank you. I'm still thinking.
Yeah, it's good.
Yeah, it's going.
Oh yeah.
Okay. So.
Okay.
Yep.
So how can I control it?
Just click the.
Oh,
keyboard.
just click. Okay.
I think it's in the way.
Okay. Okay. Does that work? Does this work?
Yep, you can clip it.
Oh, okay.
Yeah.
Okay. I just probably hold it. Okay. So hello everyone. My name is Yucheng. So today I'm going to introduce you PaleoSTeHM, a modern, scalable, spatial-temporal hierarchical modeling framework for paleo environment data. So I take this chance more like introduce me to you guys, because I haven't met one of you. So I'm a kind of new postdoc working with Bourke to this kind of project. So although you might think this is like really kind of statistical based project, my background is more like paleoclimate change during glacial cycles and paleo sea level change. So when we talk about this paleoclimate change and paleo sea level change or paleo environmental change, a big problem for us is like we want to build a complete and continuous stories from an imperfect, sparse, and spatially and temporally unevenly distributed data set. Like here, if you see here, this is a global sea level database from Kurt Lambach's paper 2014, where you see the sea level data is really concentrated in the Holocene area, and sea level data is only concentrated on coastal area in Asia and Australia and this kind of area. So the sea level, the reason why we found this kind of noisy signal is that the proxy data usually don't have direct relationships to the paleo environment. So the signal we see could be noisy. The other factor for this noisy signal we're seeing is the dating problem, because radiometric dating can provide really complicated age distribution. So that's why when we sort data, we can find the data tell us a really kind of complicated noisy signal. So there are a lot of methods we can use to reconstruct underlying signal from this noisy data. But the problem is that usually when we found the data, this data reflect a lot of underlying geophysical process. So how to partition in those geophysical process from this noisy data is a problem. And also, how do we determine which kind of model we are trying to use is another problem. So PaleoSTEHM is built for this kind of problem. So if you have kind of these issues in your own research, PaleoSTEHM may be useful for your research. So today I will instead talk a lot about like research. I will more talk about like how do we interpret data. So here's an example of New Jersey data, relative sea level data during the last 2,500 years. So we have uncertainties both in vertical axis and horizontal axis. The vertical axis is because the so much sediment relationships to relative sea level is uncertain. And the horizontal uncertainty is because the chronological uncertainty from radiocarbon dating. So this is radiocarbon recalibrated to radiocarbon curve intercal 13 and marine 13. And we assume both of these uncertainty are normally and independently distributed. This is just a simplification we made here. And the goal here, we are trying to reconstruct the trend and rate of sea level change in New Jersey during this time period. So I will use several possible statistical models to reconstruct this signal. And so, instead of going to technical detail, I will introduce the pros and cons of each method, and I will provide an example study in publication for each method, so they can actually use in many of like geological studies. So the first one, the old-fashioned and many kind of pretty like widely used method is hand-drawn method, right? You see this data, you draw a line to that data, right? So this method has really kind of, why it's popular, because it has really kind of good beneficials. It's really efficient. It takes you several seconds to do that, and it's mostly pretty accurate. So when you compare this kind of method to some statistically sophisticated method, they are largely agree well with each other. But the reason why this method is like could be problematic is that there's no kind of uncertainty estimate for this method, and so if you use this method, people will judge your interpretability, right? And in conclusion, draw from this method could be problematic. So this method is subject to could be subjective as well, right? So this method is not robust enough usually. So here's an example showing you the sea level change in China using this method by Zhong 2004, sorry. So if you see that this method works pretty well for this data set, but actually, if you compare these two plots here, they're actually sitting quite close to each other. But this method tells the sea level is, this method tells the sea level change curve in these two sites is very different. So it's clearly ignore the spatial covariance of these two sites, right? Because because if they are sitting quite close to each other, we will assume the sea level change in these two sites could be more or less similar. So the other method is linear regression method. So linear model or polynomial model, you assume the sea level or paleo environment in this site change linearly or certain amount of polynomial. Here I did it in a Bayesian style, so we have a probability distribution of the sea level change trend and sea level change rate. So everything I've shown here is done by PaleoSTEHM, and you can find the code to do that easily. I will show the link later. So the good thing about linear model or polynomial model is like computationally really cheap, so you can run it within 0.1 second, something like that. And this is straightforward interpretation. So if you reconstruct a line, you can interpret the trend, you can interpret the rates, then you can start to talk about sea level, how much sea level rise during this period, and how fast is that. But if you see that the residual plot here, you find a lot of like spatial pattern of this the residual plot here, which means our model is probably not sophisticated enough to reconstruct the background signal. If you compare to this plot here, although it's like a really simple model as well, the spatial, the residual, it looks much more reasonable here. So, but the good thing about linear model is that it's really cheap. It's really easy to implement it. So we can use this linear model to test really complicated data level uncertainty. So for example, in this study, this is one of my studies. So like use a linear model, you can test really complicated radiocarbon distribution. So you can see here, some of the radiocarbon dating can produce kind of bimodal age distribution. So some of them can occur in this area, some in this period, but majority can occur in this period. The same applies for vertical uncertainty. So here I show the coral reef living depths. So coral reefs can live, a same species of coral reef can live 0.025 meter below sea level, but this coral reef can potentially live 10 meter below sea level. Depends on the environment. So this kind of data uncertainty can be extensively investigated if we use a really simple process model like linear regression. And the next one is change point model. So instead of like we assume a single trend, single rate in the whole time period, we can assume we can break this signal into different time periods, and we can reconstruct the trend and rate in each specific time period. So this is really good for detect abrupt climate change, abrupt environmental change. So this model can tell you when this abrupt change can occur and how does the rate change during each time window. So I think probably the most famous study used this method is Kerr Lambach's post-glacial sea level curve from last glacial maximum to now. So you can see that they break the last glacial sea level change into I think 10 or 15 kind of time window, and each time window they have their own sea level change rate. And now the model before we are talking about is what we call the parametric model. So we assume a linearity during this time window. We assume certain kind of a trend during this time window. But another method is what we call non-parametric data method. Is that here's an example of Gaussian process. So Gaussian process is another kind of non-parametric method which learn the relationships between the data. So instead of learning the parameter for parametric model, non-parametric method learn the relationship between data. So for example, if two data stays quite close to each other, they are more or less correlated. So if you change one data, the other data could change if they are sitting close to each other, right? If you made a new observation, you might change your model based on that new observation, right? And And by using this kind of method, we can provide a flexible representation and also with robust uncertainty estimate for complicated signal in paleoclimate. But the drawback for this method is less easy to implement, and it could be computationally expensive for large data set and complicated data structure. And here's an example, like people use Gaussian process to reconstruct the sea level change trend in Singapore, and you can also find out the sea level change rate. And the other good thing about Gaussian process is that the relationships could be different kind of relationships, right? I can learn the nonlinear relationships. I can learn the linear relationships. So in this case, we can use kind of these different relationships defined by kernels, what we call kernels, to learn different physical process contributions to the signal we are observed. So for example, you see here, we are using a linear relationship as LT here, and ST here describe the nonlinear relationships. And if you're familiar with sea level change across New Jersey, you might find the linear relationships mostly describe a long-term geological process, something like glacial isostatic adjustment or sediment compaction or tectonic. And nonlinear relationships can relate it to more climatic effects like ocean current change or like thermal expansions. So if you see here, we can start to decompose which kind of different component contribute to sea level change here. If you see here, you can see that most of the sea level change is caused by the linear trend, but we do have a nonlinear trend here. Which is oscillated before 1500 and start to rising quickly after Industrial Revolution. And Gaussian process is also good for working with complicated data structure. So here's an example, like we are using different coral reef living depths, and Gaussian process can account for this kind of coral living depths, which is non-Gaussian distributed, right? But it could, one potential drawback is that it could be computationally expensive. So it might work for several hundred data, but like if you have like thousands of like 10,000 of data, it's probably computationally too expensive to run that. And the other thing is like, as we can infer the correlation in time, we can infer the correlation in space as well. So here's an example. If we want to infer this spatial and temporal sea level change across the North America using tide gauge data. So here is our model. So we use a global relationship. So a global relationship tells there's a global trend. Every site is the same. It's only vary with time. So this global relationships can tell us about the global signal of sea level change. And we also have a linear spatial-temporal relationships, which tells this relationships is change in space and time, which tells us the spatial and temporally varied signal, like thermal expansion, like ocean current change. This is, which is like nonlinear, and this one is linear. We have one linear and nonlinear spatial-temporal kernel. Spatial-temporal relationships. The linear can tell us a spatially varying geological process, and the nonlinear can tell us more about climatic process, right? And if we do that, we can get a spatial estimate of sea level change from 1900 to 2023 in a spatial field, and the right figure showing you the uncertainty estimate. And apart from that, we can start to decompose for each site, which kind of signal contribute how much to sea level change at this site. For example, here I show the sea level decomposition, sea level signal decomposition in New Jersey. So you can see that the reconstructed sea level signal is look like that, which is a combination of three different components. The blue one shows you the global signal, which we can interpret that as a global sea level rise trend. And this kind of linear trend probably due to glacial isostatic adjustment and local sediment compaction. And the last one the really oscillated one could be due to seasonal cycle of climate, seasonal or a decadal cycle of climate. Okay, so I will show you the last two things. Based on the same model, you can reconstruct the global sea level trend during the last 2,500 years if we include more data across the globe. And using the same model, we can start to decompose sea level components for sea level signal, different component of signal contribute to sea level change into the east coast of the US, which you can see here. Although historically, glacial isostatic adjustment is the major contributor, but when we move to 20th century, the global signal, which is global sea level rise, become more and more dominant. So here's the summary. So reconstructing physical signals from paleoenvironment data requires careful treatment of both data sites and model sites, and determining which process model to your own data could be problematic. But the PaleoSTeHM do offers several popular model for you to use only for your own data. So all of the example we use here is available in this website here, and it is built upon like a user-friendly API. So most of the model can be written in less than 10 lines of code. So you can tailor those model for your own data. Thank you.
Maybe one or two questions for you, John, and then circle back.
Very nice tool. I was wondering, so if you could work in the wavelength domain,
Mm-hmm.
can you ascribe, especially with the multiple kernels, can you have like the long wavelength being linearly related and like the short wavelength fluctuations being non-linear?
Yes. So this is a basic method. So you can define the prior for those kind of length scale based on physical knowledge. So you can specify kind of, like, okay, I want this spatial to be really kind of large scale, but this can be linear. So anything you can specify the hyperparameter to reflect your prior physical knowledge for each process.
Could I ask Mark and James to maybe join up there and see if there's any questions
Yeah.
from the private speakers as well?
Sure. Great.
And if not, we can just give you another round. Any more questions? If not, thank you again to the speakers. I would invite grad students and postdocs to join them for pizza and ask all your really hard questions about career paths, life, or academic.